Hi, hello, welcome. This is Discrete Mathematics, and today we are talking about section 3.1, functions. Now I know you're thinking, oh, I know about functions, and I know you know about functions. I expect that you've taken functions in a math class before. So today we're going to do a little bit of review about what functions are, and we're also going to start talking about them in our more mathy notation and get a little bit more theoretical with what functions are. We'll also introduce some new ideas that you probably haven't heard about before. So let's get into it. Let x and y be sets. A function f from x to y is a subset of the Cartesian product of x cross y, having the property for each x in x, there is exactly one y in y with x, y in f. So you take an x from x, you take a y from y, put those together, and that is what makes up your function. We denote the function f from x to y as f colon x arrow y. This is read as the function f from x to y. The set of x such that x and y is in f is called the domain of the function. So these are the x values, those are the input values. The set y such that x and y is in f is called the range. Those are the output values. And then we have this probably new idea. The set y is called the codomain of f. The range is a subset of the codomain. So the range and the codomain might not be exactly the same. The range are all the values that the function actually produces. The codomain are all the values that are allowed. And that's set by our parameter here, this y. That is the codomain. Sometimes the range and the codomain will be the same. That has a special name. We'll talk about that. Sometimes they'll be different. The range will be a subset of the codomain and not include everything that's in the codomain. And we'll take a look at that as well. Here we have an example, example 1. A function can be represented as a set of ordered pairs, as an equation with words or with an arrow mapping. And we're going to look at all of those. First up, function f is used set notation of ordered pairs. 1a, 2b, and 3a. That is a function using a set of ordered pairs. The domain of this set is the set x, which is 1, 2, and 3. Those are the first values in our function. And the range are the second values in our ordered pairs, a, b, and also a. But this is telling me that the codomain is a, b, and c, and the range is a and b. So here we're noticing that c is a value in the codomain. It's an allowable value for that second place, but it's not actually used by this function in particular. So here we see that c isn't a value that our function can produce. It's still part of the codomain. It's in the allowable values, but it's not actually produced by the function. Let's draw the arrow diagram. The arrow diagram would look like, here's my little circles, 1, 2, and 3. These are all the values for x. And these are all the values for y. So here's our function from x to y. And the values for y, this is the codomain, are a, b, and c. And now we're ready to add our arrows. 1 goes to a, 2 goes to b, and 3 also goes to a. So here we are seeing this is actually a function. If it wasn't a function, we would see repeated x values. So function means no repeated x values. But we see that the codomain and the range are not the same. The range are just these two, the things that the function actually produces, but c is part of the codomain. So here we see that the range and the codomain are not the same. All right, let's take a look at another example. Example 2a. Consider the function f of x equals x squared, where the function f goes from real numbers to real numbers. What is the range? And draw the graph. So this one right here, that's the domain, and this is the codomain. Is the range the same as the codomain? We'll find out. So I like to approach these types of problems if I can, with a picture. So I'm going to do some old-fashioned graphing. If you have a graphing calculator, you can use that as well to get an idea of the graph. But this is a quadratic function. Shouldn't be too hard to graph. Here's some values. I'm making an XY table, -2, -1, 0, 1, and 2. So these values are 4, 1, 0, 1, and 4. And if I would draw my graph here, this is X and this is Y. 1, 2, -1, -2, 1, 4. Here, I'll draw my graph. So my graph, oops, I missed one of my points, is a parabola. That's the shape of my graph. So as I'm looking at this, I'm seeing that, yes, it is a function, and we'll look at how to tell from the graph on the next page. It'll be a review. But what is the range? The range are the y values that my function actually goes to. And it looks like the smallest one here is 0, and it goes up from there. So our range is 0. We're going to include 0 to infinity, which is not the same as the codomain. The codomain is here represented by our axes. All the way down to here would be the codomain, but I don't have any function down there, so the range is different from the codomain. Let's take a look at B. Consider the function f of x equals sine x, where our function goes from real numbers to real numbers. What is the range, and draw the graph? So sine function is a periodic function. It's a wave. It goes between -1 and 1. It crosses the x-axis at pi and 2 pi. So this is half of the wave. Here's, let me see. This is pi over 2. Make sure I'm giving myself enough room. Here is the top of the peak, and then it comes down like that, and then it comes back up like that, and it keeps going this way. It comes down and then back up. So this is my periodic function. Sine function looks like this. So this is the domain. And this is the codomain. What is the range of my function? Where is my function actually at on the graph? It looks like it's bounded between -1 and +1. -1 to +1. Again, not the same as the codomain. Okay, let's take a look at some more graphs. This page is probably mostly review. First up is the vertical line test. A graph represents a function if and only if it passes the vertical line test, abbreviated VLT, which means that every vertical line intersects the graph at most once. So if you're able to draw a line that intersects your graph in more than one place, it's not a function. So this first one, here I am at example 3. I'm working on the first one. I can cross this graph in 2 places, so this one is not a function. I could draw a line right here that intersects the circle only once at this point. That's called a tangent line. If you ever take calculus, you actually probably already took calculus. So you probably already know about tangent lines, but that is a tangent line. But here I'm seeing that I can draw a graph that crosses in more than one place, so this is not a function. Next up is this graph. I can draw a line right here that crosses in 2 places, not a function. Next one, this looks like some sort of cubic function. I can not draw that line. Every line crosses my graph in only one place, every vertical line. Next one, I draw a vertical line and it crosses this line at every point. Not a function. Here it looks like, here I'm not crossing my graph at all, and here I'm crossing in one place, and here I'm crossing in one place. So this one is a function. If these dots were filled in, it would not be a function because I could draw and hit both of those dots. But since the dots are open, it's a function. If one of them was filled in and one of them was open, then I still could do it. But here we have both of them open, so it is a function. This one, not a function. Here I can hit it at a bunch of places. Look at that. Bam, 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 bam. Not a function. I guess I'm saying no, not. This one, also not a function. Look at that. No. Last one, this one kind of looks like a worm. Yes, it is a function. So that is the vertical line test. You've probably seen that one before. Here we are at example 4. This is a review of how to find the domain of a function. So here's your little review on domain. We have 3 cases where we've got restricted domain. I'll write all three of them over here. Draw a little like, this is like our little review. Oops. I wanted to do like a bar. Perfect. So here's our review. Case number 1 is if you've got the square root of a, then a has to be greater than or equal to 0. If we're thinking about real numbers, which we are, you can't take the square root of something negative. That gives you an imaginary number, and we're only interested in real things. So that's domain restriction number 1. Domain restriction number 2, if you've got b over a, then a can't be 0. Can't divide by 0. Domain restriction number 3, if you're taking the natural log of a, then a has to be positive. The natural log is not defined at 0 or at anything negative. So these are our 3 domain restrictions. And as I look at this function over here, I think I see all of them. I see natural log right here, so that's going to be number 3. I see a denominator, that's going to be number 2. And then I see this thing underneath the square root, that's going to be number 1. So I get to look at all 3 of these restricted domain ideas. Isn't that so exciting? Let's see. Let's look at this one first, number 1. 3x plus 5 underneath the square root, so it has to be greater than or equal to 0. And I can do some quick algebra here to solve this for x divided by 3. So x has to be greater than or equal to negative 5/3. So I'm going to put a pin in that and do my next one. Let's see, this one, 2x minus 1, x plus 4, can't be 0. Let's see, so 2x minus 1 can't be 0, or x plus 4, I guess, and x plus 4 can't be 0. I'll leave nothing. That means x can't be 1/2 or negative 4. X can't be either of those values. Last one, 7 minus x has to be greater than 0, strictly greater than 0. Subtract 7, so negative x has to be greater than negative 7, or x has to be less than positive 7. So I'm going to put all 3 of these things on a number line, and we'll take a look at what area are we talking about. Maybe make my line in green. I'm using all the colors. Let's see, here's 0. We've got a negative 5/3. We have a negative 4. I've got a positive 1/2, and I've got a positive 7. I think that's all the numbers that I'm seeing. We'll start here with our x is greater than or equal to negative 5/3. So filling in a dot, drawing an arrow to the right, that is x. Maybe I'll draw it a little bit further because I've also got that 7 to think about. There we go. Next one, purple. X can't be 1/2 or negative 4. Maybe I'll draw it in order here. 1/2 or negative 4. So it could be any of those, anything in between, or anything this way, but not those 2 values. Last one, x has to be less than 7. So open circle at 7 and the line this way. So I'm interested in the spot that all 3 of my lines are together. So I see that starts right here at negative 5/3, and it goes all the way until you get to 1/2, and then I can't have 1/2, and then it goes all the way to 7, and then I also can't have 7. So that's the area that I can have. Everything from negative 5/3 to 1/2. I can have negative 5/3. I cannot have 1/2. And then from 1/2 all the way to 7, but I cannot have 7. That is the domain. That's how you piece together all of these different restrictions that I have into one restriction, or into one cohesive domain statement. That's using interval notation. If you need extra resources on reviewing some of this domain, vertical line tests, function stuff, please let me know and I can give you some extra resources. We're going to move now to the next thing, which is probably mostly new things. So that's exciting. First up, we have modular operators. If x is an integer and y is a positive integer, we define x mod y as being the remainder when x is divided by y. You see mod a lot in computer science applications. They use a modulus operator a lot. So here we've got several examples. We'll start off with this one, 11 mod 3. So we get to do some long division. 11 divided by 3, let's see, is 3, and that's 9. remainder 2. So 11 mod 3 is 2, because 2 is the remainder when I do that division. Next one, I've got 40 mod 7. So here is 7 and 40. Let's see, 7 times 5 is 35, and I've got 5 left, and that's it. So 40 mod 7 is 5. Next up is 22 mod 4, 20, and I've got a 2 left. Let's see, so 22 mod 4 is 2. And last one, ooh, I see I've got a negative. Okay, if I go back and look at the definition, it tells me that x is an integer and y is a positive integer. So the second number in my modular operation has to be positive, but the first one actually can be negative. So the negative is a little bit different. What I'm going to do is I'm going to do negative 10, and then I want to add some number times whatever y was, the mod, whatever comes after the mod. And I want this value to be greater than 0, but I also want it to be less than whatever y was. That's y, and that's x. So I need to figure out what number I'm looking at. So 10, let's see, 1 times 6 is 6. So then I've got a negative number still, so I don't want that. 2 times 6 is 12. So negative 10 and 12 is positive 2. 2 is greater than 0, and it's also less than 6. If I would have done 3 times 6 is 18, I would have gotten an 8 out here, and that's too big. So my answer here is 2. Negative 10 mod 6 is 2. Got a lot of 2's in this one. Okay. What day of the week is 365 days from now? Here we're seeing a good example of an application for a modulus operator. Well, how many days are in a week? 7. So what is 365 mod 7? 365 and 7. Let's see, 7 times 5 is 35. 1, bring down the 5. 7 goes into 15 twice, and I get 14, so I have a 1. So 365 mod 7 is 1. So what day of the week is 365 days from now? Well, it depends on what day is now. 365 days from now is whatever tomorrow is. So we'll just do an example. If today is Monday, I don't know what day you're watching this video. Today, oops, I didn't spell Monday right. Today for me is actually Thursday. If today is Monday, 365 days will be Tuesday. So whatever day you're watching this, 365 days from your current day will be whatever the day of the week tomorrow is. Okay. We are moving right along to one-to-one functions. This is probably also something somewhat of a review for you. A function f from x to y is one-to-one. Sometimes we write out 1 to 1, usually with the dashes, or if you'd like a shorthand, you do a 1 and then a dash and then a 1. Also called injective. If for every a and b in x, if f of a is equal to f of b, then a is equal to b. And what this means in practice is that there are no repeated y values. And the way that we can look for that in a graph is we can use something called the horizontal line test. Works very much like the vertical line test, except we're drawing horizontal lines. So if we can draw a horizontal line that intersects the graph in more than one place, it's not a one-to-one function. So if we go back and look at example 3, these were the 3 graphs from that one that were functions. If a graph is not a function, it is not eligible to be a one-to-one function. You have to be a function first. So these are the ones that were functions. Are any of these one-to-one functions? This one is a one-to-one function. Yes. I'm going to do one-to-one and then a check mark. This one, not a one-to-one function. Look at that. Boom, 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 a million booms. What? An infinite number of booms. This one is not one-to-one. Last one, also not one-to-one. Look at that. Not 1-to-1. So that is the horizontal line test. Repeated y values. All right, here we go. Now we're going to do some practice with 1-to-1. Consider function f, goes from real numbers to real numbers. F of x is 7x to the 5th plus 3. Determine if this function is 1-to-1. If it is, prove it using the definition of what it means to be 1-to-1. If not, find two inputs that give us the same output. So I think I'd like to look at a graph of this one to help me kind of decide, is it 1-to-1, is it not 1-to-1? And then I can decide the strategy that I want to try next. So let's do our little graph over here. I'm going to do an XY table. I don't know how much you remember from graphing, but whenever you're graphing x to an odd power, it's some kind of shape that looks like that. X to an even power is some sort of parabola. Maybe it's an upside down parabola, something like that. But odd powers are this kind of S jog looking shape. It can be reflected or something, but it has this sort of typical shape. So let's see if we can get that to show up on our graph. -1, 0, and 1 for our x values. So I'm plugging these in here for x. You can get a calculator, but I already did this one. -4, 3, and 7 and 3 is 10. So here's my graph. 1, -1, -4, 10, 3. So let's see, at -1, I'm at -4, 0, 3, and then 1, 10. The graph looks something like that. So as I look at my graph, it looks like it is going to be 1-to-1. Oftentimes, I can't say always, but oftentimes graphs that have this odd exponent are 1-to-1. So I think I want to try the strategy of proving using the definition. The definition, I'm going to start with that. Suppose a and b are real numbers, and f of a is equal to f of b. So let's look up the definition again to see why I'm supposing this. A and b are real numbers, f of a is equal to f of b. When I defined a 1-to-1 function, I said, if f of a is equal to f of b, then a is equal to b for every a and b in x. So I said a and b were in x, and I'm saying that f of a is equal to f of b. So this is what I'm going to try to show. I'm going to try to show that a and b are the same using algebra. So f of a is equal to f of b. So that means now I'm going to pull out what my function is. 7, oops, not x, I'm doing a. 7a to the 5th plus 3 is equal to 7b to the 5th plus 3. And I'm going to try to work some algebra to show that a is equal to b. Let's subtract 3 from both sides, and then these 3's are actually both gone. 7a to the 5th equals 7b to the 5th. I can divide both sides by 7. And I get a to the 5th is equal to b to the 5th. And now I want to take the 5th root of both sides, or you can think about it as raising both sides to the 1/5 power. And when I do that, I get that a is in fact equal to b. So f is 1-to-1. This is like a little mini proof, so I'll do like a little mini tombstone. So here's just kind of on off to the side, is when you're taking nth roots, if n is odd, there's one answer, either positive or negative. If the thing that if a would have been negative, then this is negative. If b is negative, this is negative. A is positive, this is positive. However, if n is even, there are two answers. You have the plus or minus. Like when you square root something like a squared equals b squared, you want to square root both sides. You have the plus or minus, b. That's where the plus or minus in the quadratic formula comes from. So when you're doing these power ones, these ones with x's to certain powers, check the odd or evenness, because that's really going to make a difference when you're looking through these. Okay, let's do another one. Consider f as a function from real numbers to real numbers. F of x is 3x squared plus 12x plus 5. Determine if it is 1-to-1. If yes, prove it using the definition. If no, find two inputs that give the same output. So I talked about this a little bit when we did the last one. This is a squared one, x to an even power. So this graph is going to look something like a parabola. A parabola, which looks like this. So it's probably not going to be 1-to-1, is my guess. So what I want to do is I want to try to find two values. I want to find this value, where this is the same two different x values giving the same y value. That's what I want to find. Two dots on each side of that parabola. And I have different options here. I can try to solve, I can hope that the graph maybe sits below the x-axis and will hit the x-axis twice, and I can find those two values. But it's possible that my graph sits above the x-axis like this, and then I won't be able to find those two values. So I could try to set this equal to 0 and use the quadratic formula or factoring to solve for x. That strategy could work. Or I could use the vertex formula to graph this one. And I think that's the strategy that I'm going to use here. You can try the quadratic formula on your own and see if you can find two values there, but we're going to do the vertex formula here. So the vertex formula says that the vertex of my parabola is h comma k, where h is negative b over 2a and k is f of h. So I can find those two values. That'll be the vertex, and then I'll have an idea about what my graph looks like. Let's see, this is a, this is b, and this is c. Negative b over 2a is negative 12 over 2 times 3, which is negative 12 over 6, negative 2. And f of negative 2 is 3 times negative 2 squared plus 12 times negative 2 plus 5. Try your calculator for this one, or maybe you're just like really good at mental math. I get negative 7. So now I'm ready to try to graph this. Negative 2 and negative 7. So here's my negative 2. Here's my negative 7. So this is where my vertex is. This is way down here. So I am going to have two x-intercepts. So I could have used the quadratic formula and found that. But what I'm interested in now is maybe where does my graph hit what's the y-intercept? I might try to find those values. Let's see. What is the y-intercept? Let's let x be 0. What is f of 0? That's 5. That's easy to tell. So this value right here is 5. So I want to know, there is another value, the other side of this parabola that gives me 5. I want to know where is that value. I could try different values to see if I could figure it out. If I had drawn my graph a little bit like on grid paper or something, I maybe would have a better idea of what to try. This graph is pretty rough and ready. If you use a graphing calculator or something like Desmos, you could more easily find that value. But I'm not doing that. I'm just going to use old-fashioned algebra. I'm going to say, where else does f of x equal 5? So what I can do is I can set f of x equal to 5 and solve for x. 3x squared plus 12x plus 5 equals 5. So let's subtract 5 from both sides. I'm going to come over here. 3x squared plus 12x equals 0. Oops, I said 12x, but I did not write the x. Let's see, I think I can factor out greatest common factor, a 3 and an x. I'm left with x plus 4 equals 0. So 3x equals 0 or x plus 4 equals 0. That means x is 0 or negative 4. And I already have the 0 one. That's the one that I found already. But the negative 4 one is the one that I don't have. So this value right here is negative 4. So this is the part that is actually showing, proving, this is the part that is showing that this is not 1-to-1, the part that I'm about to write. How you got to this point, maybe you used a graphing calculator, maybe you use the quadratic formula, but this is the part that you need to write in order to show this. F of 0 is equal to 5, and f of -4 is equal to 5. So f is not 1 to 1. You need to show some, when you do these on your homework or on the exam, you need to show some amount of work to get to this part that I have written down in green. Maybe that work is saying, I used a graphing calculator, and if you did use that, I'd like you to draw a picture of the graph. If that's what you did, that's okay. But I need to know how you got these values. So you have to show some amount of work. This is kind of a lot of work to show, but this is, if you don't have those other tools available, this is always available to you. Okay. Just if you are curious and wanted to try to figure it out, if you do use the quadratic formula, because I did this as well, you get that x is equal to -6 plus or minus the square root of 21 over 3. So another alternative for this one is you could say, well, the f of -6 plus the square root of 21 over 3 is equal to 0, and f of -6 minus the square root of 21 over 3 equals 0. So f is not 1 to 1. So that would have worked out for this one if you had done that as well. Okay. Moving along to onto functions, we've talked about what it means to be a one-to-one function. This is what it means to be an onto function. A function f from x to y is onto or surjective. So before we had one-to-one functions are called injective, so these are called surjective. A surjective function if the codomain is the same as the range. So that means that for every y in y, there exists some x such that f of x is equal to y. And here we see our logic notation that we had back in chapter 1. For all y, there exists an x such that f of x is equal to y. So this is basically telling us we're using the entire domain. So if you're looking at a graph, something like this, where I've got arrows going up and arrows going down, I'm using this entire domain in my graph. So the codomain and the range are the same. That is an onto function. It doesn't have to look like this. That's just one example of a function that is an onto function. All right, I want to show that the function f, which is all real numbers except for 0, that's a -0, to positive real numbers, and f of x is 1 over x squared, which is a function of non-zero reals to the positive reals. I want to show that this is onto using the definition. So what I need to do is I need to show that for some arbitrary y, where y is a positive real number, there is a value for x that is an element of those non-zero reals. So here is what I'm going to say. I'm going to say, let y be an arbitrary positive real number 1 over x squared is equal to y, and I want to find x. So x squared is 1 over y. So I'm taking one step of algebra for that. I want to take the square root. So x is equal to 1 over plus or minus the square root of y. Here, this works out. X exists because y has to be greater than 0, because it has to be positive. I said it was a positive real number. Positive real numbers also don't include 0. So we've got several things going on right here. If I'm taking the square root of y, it has to be greater than or equal to 0, and it is. And since it's in the denominator, it can't be 0, and it's not because it's a positive real number. So this is something that exists. So we're safe. So I've shown here, this is the for all y part. I've said y is an arbitrary number. So far I've done some algebra and I show that this is y. What I want to do is I want to find an x that makes this true. And I can pick that value of x. And I'm going to pick x to be 1 over the square root of y. I could also pick 1 over the square root of negative y. Wait, no, I can pick 1 over the negative square root of y, because that's the other option that I'm seeing here. But I'm going to pick the positive version. Then f of x is equal to y. The alternative, or I could pick x equals 1 over negative square root of y. That would also work. So f is onto. This was kind of like a proof, so maybe I'll do another little tombstone. Look at that. There it is. It's so little. Let's do another example of onto. This is a function that you should recognize. We did this one already. We showed that this one was a one-to-one function. So how exciting. Now we get to show whether or not it is onto. Consider f, the function f of real numbers to real numbers. F of x is 7x to the 5th plus 3. Determine if it is onto. If it is, prove it using the definition. If not, find a counterexample. That's what we're looking for. And I think this one is onto. If I remember, the picture looked like this, and I just said earlier, this is actually the example that I drew. If the graph goes over the entire codomain, which is all the real numbers, positive and negative, and this one does. So I'm thinking it's going to be onto. Let y be an arbitrary real number. So I'm looking at this for deciding what y should be. Before I said positive, and that's because this was positive. So you have to watch out what are the stipulations on y, and that's what I want to put when I'm starting to write my argument. So y is an arbitrary real number. I want to find an x such that 7x to the 5th plus 3 is equal to y. Am I going to be able to do that? Well, let's try it. 7x to the 5th plus 3 is equal to y. Let's subtract 3 from both sides. 7x to the 5th equals y minus 3. We'll divide everything by 7. I'm coming over to here. X to the 5th equals y minus 3 over 7. And now I can do this 1/5 root situation, and I get x to be y minus 3 over 7 to the 1/5 power. This will map to y. So f is onto. Okay, let's take a look at the next one. This one was not one-to-one. This was our parabola, if you remember. Let's see. I think my vertex was at -2, -7. And this was 5. So I had a parabola looking shaped like this. I'm thinking, is this onto? So to be onto, it has to use all the real numbers for the graph. And it doesn't. It doesn't use any numbers less than 7. So I'm going to say, I'm thinking that this is not onto. Let's let y be -8. And I'm picking that because the graph doesn't go here. I will refrain from making a Mean Girls reference. But y is equal to -8. Then 3x squared plus 12x plus 5 is equal to -8. So I'm seeing what value of x will give me a y value of -8. And I'm going to show that there isn't one. So let's do that. I'm going to add 8 to both sides. 3x squared plus 12x plus 13 equals 0. So now this is something I could use the quadratic formula for. I'm going to take the discriminant. This is the symbol for the discriminant. That's the -b minus 4ac. That's the part underneath of the quadratic formula. And that's going to be it's b squared. 12 squared minus 4 times a times c. And I get -12, which is less than 0. And this means that there are no real roots to this equation. So that means there are no real values for x that make this equation true. There are no real values that will let 8 be an output of this function. So that means that it's part of the codomain, but it can't be part of the range. So no x can map to -8. No x that's a real number can map to -8. So that means that f is not onto. Whoa, the tombstone got really little. And that is the end of this one. Okay, let's revisit the same function that we had in A, 7x to the 5th plus 3, but let's change our domain and codomain to be only positive integers. And I'm going to show that this is actually not onto. Here we saw that it was onto when we could have real numbers to real numbers, but now we're only interested in positive integers to positive integers. So we need to look for a counterexample. And if I'm going to draw a picture here, let's redraw this picture. Oh gosh, I think I got rid of it earlier. Okay, this is 3, and this is 10, and this is -4, I think. And here I've got -1. So it was something like this. It crossed here at -3 and right there. So what I'm interested in is positive z to positive z. Where is that? That's this area right here. And what I'm seeing is I'm seeing this gap between 0 and 3. So the function exists there, but it doesn't exist in positive integers. There, like I have to put in something negative for x in order to get these values. And so that's where I want my counterexample to live. So I'm going to pick y is equal to 1 because I can see that my function is not defined in this little positive quadrant at that point. So y equals 1 is a positive integer, which it has to be as per this stipulation right here. F of x is 7x to the 5th plus 3 equals 1. I'm setting it equal to 1. And I'm going to solve for x. And I'm going to see what value for x gives this value for y. And I'm going to show that it's actually not in this set right here. So 7x to the 5th is equal to -2. I did a -3. Now I'm going to divide by 7. X to the 5th equals -2/7. I'll do my 5th root. So x is equal to -2/7, the 1/5 power of that. And this is less than 0, which is not a positive integer. So it not only is it not positive, it's not even an integer. So like this is double whammy. F is not onto. That is my counterexample. You could have chosen other counterexamples. I could have, instead of picked y to be 1, I could have picked y to be 2. And that also would have not worked out. Actually, I think those might have been the only choices, 1 or 2, because I had to pick an integer that was positive. And once I get to 3, my function actually, it does work out at 3. So you had to pick 1 or 2. All right, let's talk about bijective functions. We've done injective, we've done surjective, so now we're doing bijective. A bijective function is both one-to-one and onto. So it's very special. If a function is bijective, then it has an inverse function. And an inverse function takes your xy pairs and it makes them into yx pairs. We use this notation, F inverse. If you're solving for an inverse, what you do is you say y is equal to whatever your x is. Let's say it's 3x squared plus 5. And then you switch x and y, and then you solve for y. So you would say that x is equal to 3y squared plus 5, and then you would solve until you have y equals something. And then this is your inverse. So that is a very quick, very rough review of how to find an inverse function. If you're doing it algebraically, we're going to do a mapping one here that's a little bit not quite so much algebra. In example 9, if f is equal to the set that contains 1, 3, 3b, 1a, 3b, and 6c, determine if it is bijective. And if it is, what is the inverse? So here we go. I've got 1, 3, and 6. And I've got A, B, and C. Let's see, 1 goes to A, 3 goes to B, and 6 goes to C. So it is bijective because it is one-to-one and onto. One-to-one means there's no repeated x values. And so I'm seeing that here And for it being onto means it uses everything that's in the codomain is also part of the range, and I'm seeing that as well. So what is my inverse? The inverse is the set that contains ordered pairs A1, B3, and C6. That is my inverse. I'm flipping all of those pairs. And I have a note down here, the graph of y equals f of x and the graph of y equals f inverse of x are mirror images about the line y equals x. So I'll maybe draw one example. If you look at x squared, but we're only going to look at the positive part, because if you do this, then it's not a function anymore, or it's not a one-to-one function, and I want it to be one-to-one. So I'm only going to look at the positive part. And then this is the square root of x. These graphs are a mirror image about the line y equals x, so they reflect across that line. Okay. Next up is composite functions, function composition. This might also be a little bit of a review for you. Let g be a function from x to y, and let f be a function from y to z. So x to y is g, and y to z is f. Then the composition from x to z is called f of g, which we write with this little open circle symbol, or you can write it as f of g of x. So here in example 10, I have a table that gives some information about f and g, and I want to complete the table for f of g. So f of g of x is f of g of x. So f of g of 0, first step would be to find what is g of 0. You start on the inside. F of g of 0, well, g of 0 is 8. So what is f of 8? So I did that. F of 8 is 21. So this one is f of g of 1. G of 1 is 5. F of 5 is 30. And I can fill out this whole table. G of 2 is 9. F of 9 is 18. G of 3 is 6. F of 6 is 27. And G of 4 is 7. And F of 7 is 24. So that is composite functions. Very quick review of those. Let's talk about the binary operator. A function from x cross x to x is a binary operator. It's called a binary operator. Binary meaning 2, because I'm taking 2 x's and I'm turning them into 1x. So a common binary operator would be something that takes r squared and turns it into r. The thing is, all of these have to be the same. The set of x is the same for everything. So you can't say, well, let's do z squared to r. That's not how it works. They have to be all the same. So you could do z squared to z. That would work. A binary operator f on set x is commutative if f of xy is the same as f of yx for all x and y. So some common commutative operations are adding. So 3 plus 4 is the same as 4 plus 3. Another one is multiplication. 3 times 4 is the same as 4 times 3. Those two are commutative. Division and subtraction are not commutative. Here in example 11, determine if the following are binary operators, and if they are they commutative? So let's see, x is r. So this takes r, and does it turn it into, so the thing is does this result in something that's a real number? 3 times a real number squared times another real number. Is that going to be a real number? Yes, it is going to be a real number. Let's take a look at the next one. If this is a real number and this is a real number, oh, sorry, we're not doing real numbers. We're doing positive integers, z plus. If this is a positive integer and that is a positive integer, is the sum of those two going to be a positive integer? Add 2 positive integers together, you're going to get another positive integer. How about x minus y? If you take a positive integer and subtract a positive integer, will you get a positive integer? Sometimes, but not always. Let's let x be 1 and y be 2. Then 1 minus 2 is -1, which is not a positive integer. So this one is not a binary operator, but the other two were. So let's go back and answer the second question. Are they commutative? Let's see. So I think this first one is probably not commutative. Let's try, what is f of 1, 2? If it's not commutative, I just need to find one example. That's 3 times 1 squared times 2, which is 6. What is f of 2, 1? That's 3 times 2 squared times 1, which is 3 times 4, which is 12. So those are not the same. Not commutative. But addition is commutative. So x plus y is the same thing as y plus x. So yes, it is commutative. Okay, let's take a look at our logical operators. They are also binary, and, or, and implies is binary. And let's take a look at that. So our set now, before our sets were real numbers, this set was positive integers. Now my set is values, true and false. Those are the only two values that are allowed in X. So this takes on a value from X, either true or false. And this takes on a value from X, either true or false. Does the result take on a value from X? Is the result of this going to be from the set true or false? And the answer is yes. So yes, this is a binary operator. But is it commutative? Let's take a look at, what about if I did evaluate my function at values true and then false? Then that's going to be true implies false. And that is actually false. What about evaluating my function at false and then true? So this is the opposite of this. False implies true. What truth value does that have? True. These two are not the same, so it is not commutative. All right, last one, a unary operator. A function from x to x is called a unary operator on x. So that would be something that takes real numbers and goes to real numbers, like f of x to x, where f of x is, and this is the x from up here, not x. So this value takes either a true or false value, and it returns either a true or false value. Okay, and that is the end of this session. See you next time.